All right, so we're looking at how to calculate a chi-squared test statistic. There are lots of different things that go into looking at what kind of statistic you've got. It really depends on the data that you have. You might recall from class, from your stat class, that there are several different kinds of chi-squared statistic. Let's get the right size here. Chi-squared test, I should say. But every chi-squared revolves around the difference between what you observed and what you expected. So a chi-squared takes categorical variables and then changes them into puts that stuff in a two-way table, and then we use that two-way table to compute the chi-squared statistic and then make the right conclusion. So let's look just in particular at a few examples. So let's say that you are looking at a set of like jelly beans or something, and you know that these jelly beans come in three colors. Let's just say that the three colors of the jelly beans are red, yellow, and green. So you know that red, let's say that red jelly beans make up 40%. And let's say the green jelly beans make up 30%. And let's say that blue jelly beans, I don't know if blue jelly beans are particularly appetizing, make up 20%. And then there are orange jelly beans, and they make up 10%. Right? So let's say that you have a sample of 200 jelly beans. Okay, so if you've got 200 beans, then what you expect for each one of these is these percentages. So 40% of 200 is 80 beans, last time I checked. You'd expect 60 green beans, you'd expect 40 blue beans, and you'd expect 20 orange beans, and just check and make sure that those all add up to 200. Then let's say that what you actually got, and so you got this sample of 200 random jelly beans off the out of a bag or off the factory line, and then what you actually get is what you observe. Okay, so let's say, just for the sake of argument, that you have 90 beans, 72 beans, that's 162. Let's say then you got 30 blue beans and then only 8 orange beans. Okay, so this is what we call a chi-squared goodness of fit test. One second here. In a chi-squared goodness of fit test, you're checking to see whether the observed proportions are equal to the expected proportions. And so to calculate this test statistic, what you're always looking to do is to basically sum up the all of these differences. So the chi-squared test statistic is the sum, and I'm not putting any fancy things on here, of just the observed minus expected squared over the expected. Okay, and your calculator actually takes care of a lot of this for you. We can talk about how to put it in your calculator, but basically what you're doing here is you're finding these differences and then squaring those differences, dividing each difference by the expected count. Each of these things is called a contribution. So let me color code here for that. Okay, so just real quick, we've got. Okay, so I'll try to color code here and look at each of these contributions here. So you've got the observed minus expected is for the red jelly beans is 10 squared. So observed minus expected is 10, so 90 minus 80, and you'll square that quantity. Okay. For the green jelly beans, the observed minus expected, so we're going to add that. For the green jelly beans, the observed minus expected is 12 squared. out of 60. Okay? Then for the blue jelly beans, that is a -10 quantity squared over 40. And then for the orange beans, it is another -12 squared over 20. Okay. And so we're going to add all those numbers up. Just bear with me here. And that chi-square test statistic is a whopping number. It's 13.35. Okay. Now, for a goodness of fit, the kind of test you're running, you remember that you need to figure out the degrees of freedom of this test. We've got all these different categories, right? So we have 4 possible categories that these fall into. So you would run this test with 3 degrees of freedom. And chi-squared only increases. Chi-squared is a left skewed distribution, which has a shape roughly like that. And then, let's see. So you'd run the chi-squared curve, and then you'd find the probability to the right of 13.35. Your calculator automates all of that for you. But that's the basic structure of how to compute a chi-squared test, and or chi-squared test statistic is what you asked about. So let me make sure that yeah, I can make that a little bigger. I think my screen's too big. I think that's what's going on. Still on that. Let's focus that. Okay, does that help? But yeah, when I switch screens, I forgot to focus the other screen. I will get better at that. Okay. So that's how you calculate a chi-squared test statistic. Now, remember, there are several different kinds of tests that depend on the hypotheses that you're carrying out. Okay. And chi-squared is not a huge portion, effectively not a portion at all of this year's exam, but it might be something that you're curious to know for AP Bio or something along those lines. So let me put this back in focus here so that you can get one more look at that. And so that's what we're looking at for how to calculate a chi-squared. Okay. All right, so what I want to do is move to the next question. We're looking at how to tell whether a problem is a difference of what I suspect is 2 means or a matched pair. So let me finish this question. Okay. Okay, so the question we've got here is matched pairs versus difference of means. And that's what we'll go into now. Right. So let me talk through that first, and then I'll put some numbers up. So the difference between a test for a difference in the means of 2 different populations and a matched pairs mean is really whether a lot depends on whether the samples are really independent. And so there are really 2 different kinds of ways that you could set up your data collection that will sort of dictate the difference between these 2 situations, right? So let's say that and a lot also depends on the experimental design. So a good rule of thumb is basically the following. If you have a completely randomized design, so you have a bunch of subjects, right? And then you split them, you randomly assign the treatments. So you randomly assign them to treatment A and treatment B, and then your goal is to compare. Like, for example, maybe you gave them 2 different kinds of training, and then checked how well their reading speed improved over the course of the training or the instruction. So let's say then we were going to compare means. Then this is a 2 sample t-test for the difference in means. Okay, so you got a 2 sample t-test for a difference in means when you have a completely randomized design. You will have a matched pairs when what you're doing is blocking basically by sets of 2, or you're blocking in and of themselves. So I could draw a diagram for that, but it's kind of better if I say, like, so here's the kind of thing that would be, let's see, let's draw, let's do this. Okay, so let's say that you and a bunch of your friends get together and you go to an amusement park, right? And then you want to know whether you think ride A or B is more popular. Ride A is more popular if it has the longer wait time, and assume that both of wait times mean the same thing for both rides, basically. And so you and a bunch of your friends randomly split up times, and you're going to both enter these rides at the same time. And so you're going to pull, and you're going to pull like I want to make this is a very small sample, but let's say that at the first random time that you all decide to do this, so like let's say you randomly pick like 10, 11 a.m. and you're both going to enter, like you're going to have one person in your pair enter ride A, then another person enter ride B, and let's say that there's a 10-minute wait at ride B and an 8-minute at ride A, and an 8-minute ride wait at time. Sorry, let's start again. A 10-minute wait time at ride A and an 8-minute wait time at ride B. There we go, words. Okay, and so that is what happens at the same time. Okay, so let's say that you collect this data throughout the day. At different randomly selected times. Okay. And so if I'm looking at these 2 sets of data, I may not know that what happened was that I collected these data by going at the same time. So these are at random time 1, and these are at random time 2, and these are at random time 3, and so on and so forth. So what I actually did is I made this measurement at different randomly selected times that are not independent. Okay, so the analysis for this would be a matched pairs. The analysis for this would be a paired t-test. Okay, and another time that you would use a paired t-test would be if you had a design where you had a bunch of subjects and you paired them off by similarity. And then you flipped a coin, and then one of them got treatment A, and the other one got treatment B, and then the other one got treatment A, and the other one got treatment B, and so on and so forth. And what you did is you compared the difference between these. And what happens in this design is that the differences make up your data set. Coming back up to here, when these 2 things are not independent, neither of these data sets are what you want to use. What you really want to use is the difference, which you will, of course, clearly define for your reader, right? So that they're not guessing what you're doing. And so really what's happening here is that you're taking 2 very similar times, comparing them, and that the differences are your single set of measurements. So this is, both of these cases are what you get for a paired t-test. Now, I want to point out that you might collect this data as a result of like this set of ride data that's sitting in this table. You might collect this data just by 2 random samples, right? So if I had collected ride A just by going at 6 random times, and then I collected ride B by going at 6 completely different random times, then that wouldn't be a paired t-test. Here you'd be talking about a more completely randomized design that would require you to use a 2 sample t-test for a difference in means. So hopefully that makes sense. Right. And there we go. Right. I got a few things I generally like to talk about, and then we can go through some other problems if people don't have questions they want to ask. But feel free to use ask a question to ask a question of me, or put it in the chat so that I can see it. Right. Is Bayes' theorem in AP Stats? Okay, well, not I mean, kind of, but you don't ever really call it Bayes' theorem in the course in particular. Let's talk a little bit about what Bayes' theorem is. I'll put that question in the chat as well, and I'll give you a very brief discussion of Bayes' theorem, what it is, and like how it's not like very literally in it, but conditional probability is a very big aspect of it, and you will use Bayes' theorem. You can derive Bayes' theorem from what's given on the formula sheet, and you can also kind of use Bayes' theorem without knowing that you're using Bayes' theorem in like a tree diagram type problem. So I'm going to go ahead and ask this question here, and I'll put it. I'll give it a go here. All right, so let's first talk about what Bayes' theorem. There's a fairly straightforward statement of Bayes' theorem. It's not directly on the formula sheet. Let me show you what is on the formula sheet first. In order to do this, let's see if I can navigate the closing of the video this time a little bit better. And let me see here. Let's do tabs. Where did I had a I had the formula sheet up in a second. So let's let that turn. Okay, there we go. Okay, so you should at this point be able to see a formula sheet, and there we go. We got it this time. All right, you should be able to see a formula sheet. And on the formula sheet, you will notice that the two of the very first formulas are these probability formulas. So take a look right around here, this spot, which I'm hopefully high, which but you can kind of, well, you can't really see it, but it's this conditional probability formula that I will put up here on. Let me switch over to the whiteboard. This P of A given B formula, that's a big part of what Bayes' theorem is, and I'll actually talk about what that means. So let me show you where we're going with that. Unshare that and go back to the whiteboard. That's not what I meant to do. Okay, so Bayes' theorem is can be like I said, gotten from using what you have what you have on the formula sheet. Okay, come on, there we go. Okay, so the formula sheet has the following really helpful formula, which is a good definition for conditional probability. The way I like to think about conditional probability is that the probability of A given B is the joint probability, or the probability of A and B together. And this, what I like to do is I think about this over B. I think about that as a denominator, right? And so that tells me that P of B should go in the denominator. That's what's on the formula sheet, right? And so what you can do is the following, because it doesn't really matter which thing you call A or B, as long as you switch them properly. You do not have to, again, I want to emphasize, you do not have to use this formula or this theorem like directly like on the exam, but it might actually, there are a couple of cases where you could use it to calculate the answer. So as long as you have this formula, you'll be good to go. Okay, so we've got P of A given B and P of B given A, and you'll notice that both of them involve this guy here, right? Because both of them involve that P of A and B, you can actually write P of A given B times P of B equals P of B in A times P of A. Okay. And then you can rearrange this to form Bayes' theorem. And what it basically lets you do, this theorem is used often to, if you have an estimate for some of these different probabilities on the right hand side, then you can use them to predict the probability or come up with an estimate of the probability that you wanted to on the left hand side. Let me put some words on that for you. So for example, let's say that you know that I mean, here's the simplest way we can talk about it. Okay, so I would like to know basically like what the probability is that if you have a drug test, for example, that let's say that you want to know what the probability that someone is a drug user given that their test is positive, right? What this lets you do is basically the following. You can replace these events like so, and what you can do basically, like in this case, let's say that you happen to know how good your test is. You might know that your test, for someone who is a drug user, you might know that your test is 99% accurate. You might also know that like let's say that let's see what's the right thing to do here. Let's say that you also know like what percent of people are drug users. You can predict the percent of positive tests you're going to get, and vice versa. This kind of thing typically shows up in a tree diagram. What ends up happening here in general for these is that you have to know like the total percent of probability, like positive tests. That would be something that you get by analyzing all of your data and looking at how often a test comes back positive based on what you know. And so this is what this is going to be is I actually think I should go ahead and expand this out just for completeness. So this is going to be the probability of a positive test is going to be this thing that you know on top. It's actually going to be the numerator. And then it's going to be the sum of that and the probability of a positive test with a non-user, right? And there should be a probability there. Okay, so you can, with that in mind, if you know what your test does, so like you in a lab might know these three conditional probabilities or have a guess as to what these are, but you might not know exactly what percentage of people are users, right? And so if you guessed what the probability of somebody being a user was, then you could predict the probability that your test will successfully detect a user of a drug, given that they really are a drug user, or given that the test came back positive. Sorry. Okay. Right. So that's Bayes' theorem and how it could apply to AP Stat. The things in yellow that I highlighted are things that are things that you would know as maybe the maker of a test, right? That you would know these things as the maker of a test. Because you did it in the lab, you put it all together, but you may not actually know the probability that people really use drugs, right? And so your estimate of how often that your test is actually, your positive test actually detects a drug user depends on your estimate of how many people actually use drugs. And so a more sensitive test is required for a rarer thing. So if there are a lot of drug users, if there are like 10% of drug users and 99% sensitive test for drug users is going to totally find that difference. But if only 0.1% of people are drug users and 99% a test that gives 99% true positive and let's just say true negative result, that would actually be a little bit problematic, right? So that's a thing that sometimes will show up in a stats class. That's kind of the rare condition or the rare disease problem. That's a thing that does tend to happen. Okay. All right. Okay. Car owner virus asks. I just said it out loud. I get it now. Which linear transformations are best for which situation? Okay. That is a really fine question. Let's see. We kind of need to pull up some data. And again, this is another thing that is going by the wayside, given the changes in the AP Stat exam due to school closures. I'll answer this question kind of honestly, and then I will answer this. Then I'll answer kind of. Let's see if I can make a more systematic answer. Honestly, I try a lot of things, right? And so what I might want to do is look at the data and see whether the residual plot, when I transform the data in some way, whether the residual plot indicates that that's a reasonable transformation to do. Sometimes you'll find that when you do a transformation on one variable and not the other, you don't actually get something that is really still truly linear. I'm gonna pull some data from a textbook, and then we'll talk through that a little bit because I think it's important to have an example. But the question then also becomes, like you asked, how do I know which transformation to use? And the transformation to use, I think, just depends on which transformation you use provides the thing that you can actually analyze. So let me grab some data because I find it hard to make this. This is something I do find hard to make up on the fly. Right. So let's see. All right. Let me look for a set of data that require a transformation to show an example. Okay, so let me. Okay, let's talk about a set of data here. So bear with me here. All right, so you should see a website. This website is called staplet.com. No matter which textbook you use, I programmed this for statistics, with probability and applications, 3rd edition. But you can also use it for a lot of different kinds of analysis. It doesn't really matter what textbook you're using. And so what I want, the goal here is to pull up a set of data that that doesn't. I'm trying to pull up here a set of data, and my internet's letting me down here. I'm trying to pull up a set of data that that has that needs a specific transformation in order to be there we go, specific transformation in order to be linear. I'm just going to call this set A, and so I'm going to put my data in here. And then I am also going to, so my explanatory variable is A, and then I am going to put in another set of data here. So you can see just by what I'm doing here that these data have a negative relationship. The larger the explanatory variable, the smaller the response variable. Okay. So you can see this lovely scatter plot here, hopefully. Okay. And when we try to do a linear regression, we see that the residual plot for that shows a bend. Right? There we go. Now it's working. Okay. We can see that there's a big bend in that residual plot. We might try other kinds of transformations. Okay. So let's say that we thought, well, this looks to me like maybe it's a quadratic model. And you can see the residual plot still has weirdness going on with it, and has has kind of a wavy pattern to it. This could be a good model. Okay, and so really, here's another try. Let's look at maybe let's see what happens if we did an exponential model. Okay. In this case, the residual plot, this one shows a little bit more of a bend to it. So I'm fairly comfortable with this first model. Let's take a look at this. Let's go back to this model here. Okay, and here I'm kind of jumping. I'm going to the end here. Yeah, let me do. Do you want me to do one over? You want me to do one over the explanatory? Is that what you want to try here? Because we can try a bunch of different things. You just need to be patient with me while I put the data in the calculator. Okay, so. I will say, practically speaking, look at A. Look at the explanatory. You can see that one of the explanatories is 0. So 1 over isn't necessarily going to do the trick. Also, like if I were to try to log transform the A variable, it wouldn't really work either. I generally only try two things. I generally only try the log of the response, the log of the explanatory, or the log of both. In this case, given the response, what I want to do is I want to replace the let me replace just for the sake of mechanics. Let me replace the response variables. Let me replace the response variables with their logarithms. Okay, so all I'm going to do is I'm going to take the log base 10. You could do this with a different logarithm if you wanted to. All I'm going to do is take the log base 10 of each of those numbers. I'd need to do a little bit of calculator magic, and then I will put those numbers in there for you. Okay. So what I'm going to do here is I'm going to replace this with I'm going to call this log b. Okay. And all I'm going to do here is I'm going to replace this. Yep. I'm going to replace all these numbers I have here with their logarithms. Okay, so let's do 0.903. Okay, so this is the most interesting part of the stream, where you just listen to me talk while I type numbers in and not look directly at you. So hopefully you're understanding that. Okay, there we go. And then, so 0.38021, 0.30103, 0.20412. And again, as much as possible, I really like using technology to do these kinds of things, but you can, use, you could do it the old-fashioned way if you like. And then when I do a linear model on this, so I'm going to do a linear model on this data. You can see I get basically the same residual plot, just at a different scale. And what's most important here is the equation, right? So this says that the predicted value of y, the predicted value of log b, is 10 raised to those 10 raised or log. Let me copy it over. Okay, so you can see that equation there that I've got. So let me go ahead and let me move over to the whiteboard and let's talk about how to work with that. Okay. I need to. It's very helpful, but I need to focus this screen. There we go. All right, so let's take a look. Okay. So I have from the transformations, I found that when I graph like the predicted value of log y is 0.9003 minus 0.0504x. And so if I raise 10 to both sides, right, that's gonna undo the transformation, right? So this is and so this is 7.948. So I also want to point out that this is 10 to the 0.9003 over 10 to the 0.0504x, right? And then so what you can do is if you use a log transformation, then you can get a power law. And so this is 0.7948 over 10 to the 0.0504x. Let's see. All right, looks like I did let me check something real quick. Right, and so yeah, so I can use this to change to a power law essentially. And so what I've got here is this is 1.123 to be x, right? And so what you have here is something along the lines of a power law transformation. I don't know if that answers your question. You could do a little more algebra on that. Again, the good news is we don't really have to worry too much about that for the exam in its current configuration. Yeah. So yeah, practically speaking, it's just which one produces the linear transformation. I find it hard to look at the numbers without. I need to look at the numbers and really kind of just kind of predict what's going to happen. But I know that if I see 0 in any of the data, it's going to be hard to use a log transformation on that particular variable. You could shift all the variables over, but that makes there are a lot of different ways that you could do that. But you can try a lot of different things. There is a suggestion that you can, for example, one thing that's basically, I would start if you are if you're going to do powers, then basically, there's it kind of depends on what you're looking at and what the shape of the function is, and what values they take on. For example, if you have a left skewed distribution, you might try squaring the data. I always like to use logarithms just to start, because it just tends to solve the problem pretty well. And generally what'll happen is if a log of both sides changes the data to linear, you'll get a nice polynomial-ish thing. You get an exponential model if you only transform one of the data. I think I said power before. I think you're getting an exponential model there. You transform just the response. All right. Any other questions? We're a little all right. In the absence of particular questions, again, for those of you who are still who are kind of here, would you rather see, if you have an opinion on whether you would rather see something that is more quantitative, like doing a problem that involves, like how to do problems that involve numbers, or whether you want to talk more about writing and writing responses? I think one of those two things would be a good topic at this time. I'm going to kind of go into them. I'm going to go into the latter if nobody has an opinion on that. All right. I just want to talk a little bit about what what I think here's some things. Let's see. Let's do this. Okay. There's a lot of what seems like mechanical writing on the AP exam. There are a lot of templates for things like how to write the conclusion to a hypothesis test, or how to interpret a confidence level, or how to describe a distribution, or how to compare two distributions. But I think just in general, as you're trying to figure out and write responses to questions that you have that are kind of unusual, like if you're looking at a free response thing, or you're comparing two new products, and you have data on how those products affect, like, the gas mileage of cars, or how they affect the energy efficiency of a home, then when you write up which thing you would choose and why, you definitely need to think about whether the answer you give is both numerically correct. So, for example, like, did you use the correct numbers? Did you calculate the mean correctly in each case, and then are you correctly comparing the means? But also that your responses should be based in good statistical practice. Your responses should reflect an understanding of what statisticians do and how they think about data. So, for example, is that data categorical? So that means that tells me how to analyze the data. If that data is numerical, then that tells me something different about the tests I use for sure. But also, just as I collect these numbers, what are the methods that are used? What are the things that are done that what are the things that are done that a statistician needs to consider? Like, for example, is the way that I ask a question going to influence the response that a person may have? Like if I'm conducting a survey, determining whether people support their local police departments, and I have a police officer in uniform conduct that's going to really affect the question. And so basically, when you're writing a comparison between two things, not only do you need to have the right numbers, but you need to make sure that a statistician would actually do the things that you're actually looking at, whether those practices are correct. Okay. So those are just some ideas I have about writing. If there are no other questions, then I'll also talk about what I mean by that in relation to an actual question, a free response question. All right. Okay. So if we're looking at how to write, and there's not a lot that we know yet exactly about the kinds of items that are going to be on the new AP Stat exam, but we're not even sure really how many free response questions there are going to be, but we do know it will all be free response, and the items will be such that you'll have to use critical thought and higher level skills to answer those questions. What we're kind of like lucky to have in AP Stat is a bank of what we call investigative tasks, which typically in the AP Stat curriculum are the sixth free response question. So just to give you an example of what I mean by writing responses to this kind of a question, I want to look at some of the parts of a question 6, and then this is also this is going to be last year's released question 6. Also, there are some really good fun statistics in this particular example as well. So let's briefly take a look at that. Yeah. Okay. So in a question 6 always consists of a couple of things that you know how to do, and then a couple of things that are new. And so in particular, if you're looking at writing the answers to 6A and 6B. So if we're looking at this graph here, and it's basically you want to know what this is a graph of, and so the problem stem tells us that this is a random sample of rental prices for 50 one-bedroom apartments taken from a website where people voluntarily list available apartments. And then you're first asked to describe the population for which it is appropriate for Emma to generalize the results from her sample. Okay, so we're looking at a question like this. You probably have there are two things that the randomization takes place in statistics. There's random sampling, and then there's random assignment. Okay, random assignment to treatments is cause and effect, but random sampling is really what's happening here. Okay, and so when we talk about this. This is a random sample of a population. This is a random sample from a group. So what we need to do is figure out what group was sampled. And we're looking at that, and it says from a website where people voluntarily list available apartments, and that's actually going to drive a lot of what we're doing here. So Emma did a random sample, yes, but she did a random sample out of just the things that were on this website. And so it's important to think about the practice. Like imagine Emma doing this, and then also look at what we're what we hope to do. The population of interest might be 1-bedroom apartments in the whole city, but that's not where we sampled from. We just sampled them out of this website where people voluntarily listed their apartments. So really what we've got going on here is that the population for it's appropriate for Emma to generalize her results is just the population of rental prices for this particular website at the time that she did this procedure. And that's different than the population that she may have actually wanted to study. But that's what she did. And now we look at part B, where it says Emma wants to estimate the typical rental price of a 1-bedroom apartment in the city. And based on the distribution shown, what is a disadvantage of using the mean rather than the median? Okay. And here we see that this distribution is skewed. Okay. And this distribution is skewed to has the tail on the right. This distribution is skewed right. And what's actually happening then is that the mean is going to be pulled in the direction of the tail. And so when you write this up, you don't want to just write the mean is going to be larger than the median because the tail is on the right, right? There's more that you can say about this problem than that. Okay, basically, what the mean does is it takes all the numbers into account. Sometimes we like that because we need to know, like we use the mean in a lot of our computations when we do significance tests and confidence intervals, because it does have takes the entire distribution numerically and mathematically into account. But if we want to really know what people experience, if we want to know what the typical middle number is, we really should use the median. Okay. And so when you write a question like this, you not only have to correctly identify that the mean will be larger than the median, it would be appropriate for you to say that the median is a more accurate representation of the rental prices that people actually experience. It is not influenced by a few really, really large numbers that are on the right side of the distribution. Okay, so you have to understand both what the numbers say, and you also have to think about what a statistician does when collecting this data, and how a statistician would analyze the different numbers that they're given. Okay, and so you could even ask the question whether this is an appropriate, entirely an appropriate method to use. Certainly, it was not as difficult for Emma to do it this way. She would have had to do a true random sample of apartment prices in the area she was looking at. She would have had to cast the net a lot wider. It's harder. Sometimes it's harder to do the statistics that you expect to do, but you can still get a fair amount of mileage out of what you have available to you. All right, we're coming up close to the end of the hour here. There aren't any last minute questions. Then what I want to do is go ahead and bring this train ride to a close here. Want to again thank you for coming to our session today. Questions and answers on the AP exam, AP Statistics exam.